A magnitude 7.5 earthquake. The ground suddenly rises nearly 23 feet, about the height of a two-story building. Water in the bay is pushed upward. Within minutes, a wave rushes toward the shoreline. This may sound like a computer model or some worst-case scenario built to scare people. It is not. It already happened, right beneath the place where Seattle now stands. The fault runs close to downtown. It cuts through areas near the waterfront, the stadiums, neighborhoods, and some of the most recognizable places in the city. People walk over it every day without thinking about it. They drive to work. They drink coffee. They sit in traffic. They watch games. They look out across the harbor. And beneath all of that is a shallow fault capable of producing violent shaking very close to the surface. That detail matters. A deep earthquake loses energy as the waves travel upward through the earth. A shallow earthquake does not have much distance to travel. The force reaches the surface fast, and it can hit hard. That is what makes the Seattle fault so different from the distant earthquake most people in the region have heard about. This one is not far offshore. It is right under the city. The last time it ruptured, there were no glass towers, highways, packed stadiums, ferry terminals, or power lines. Much of the area was forest. Native communities lived along the shoreline of Puget Sound. Today, millions of people live across the region. So the real question is not whether Seattle has survived earthquakes before. It has. The question is, what happens when a modern city is built over the remains of a disaster that almost everyone forgot? And what happens if the ground decides to move the same way again? Here's the part that really caught my attention. Most of the Seattle we see today was built before anyone fully understood the Seattle fault. Until the early 1990s, it wasn't even treated as a major hazard. On many maps, it simply wasn't there. That changes how you look at the city. The older buildings weren't designed with this fault in mind. Not because the engineers were careless, they worked with the best information available at the time. You can't design for a danger that nobody knows exists. That's how engineering works. Building codes are always based on what people understand in that moment. As science improves, the rules improve too. But cities don't rebuild themselves overnight. Even after the fault was identified, Seattle couldn't just tear down thousands of buildings and start over. That's not how the real world works. Strengthening old structures takes years, huge budgets, and difficult decisions about what gets fixed first. So, this isn't really a story about someone making a terrible mistake. It's a story about how knowledge changes. People naturally think of the ground beneath their feet as something permanent. We expect roads, buildings, and neighborhoods to stay exactly where they are. But the Earth doesn't measure time the way we do. 100 years feels like history to us. To a fault, it's almost nothing. More than 1,000 years passed without another major rupture. That's long enough for entire civilizations to change, for cities to grow, and for generation after generation to believe the danger was gone, or maybe it never existed at all. By the time scientists finally recognized what was hiding beneath Seattle, the city had already become one of the largest urban centers in the Pacific Northwest. And that leads to the next question. If this fault stayed quiet for so long, what finally convinced scientists that a massive earthquake had actually happened here in the past? This is where the story stopped feeling like a theory and started feeling real. It all began with something that simply didn't make sense. Scientists found dead trees standing upright underwater, not fallen over, not scattered around. They were still rooted in place, almost as if time had frozen the moment they went under. That alone was strange. Then they found something even harder to explain. Thin layers of sand buried beneath the soil, stretching across the land where sand shouldn't naturally be. They found seashells and other marine remains sitting several feet above today's shoreline. They even found an ancient beach sitting far higher than any normal tide or storm could ever reach. None of those discoveries made sense on their own, but together, they told the same story. The trees were still standing because the ground hadn't been washed away from somewhere else. It had suddenly dropped or shifted while the forest was still alive. The sand showed that a huge wall of water had rushed far inland, left its mark, and then pulled back. The raised shoreline showed that part of the land had been lifted upward in a single event, not slowly over thousands of years. Then came the dating. Different samples from different locations all pointed to roughly the same time, around the year 900. That's the moment everything started to line up. When several completely different pieces of evidence all tell the same story, coincidence becomes very hard to believe. But what surprised me most wasn't the geology. It was the people who had remembered. Long before modern science connected the pieces, the Duwamish people had already passed down stories about a day when the ground shook so violently that the shoreline changed. They described the water pulling away before rushing back. They talked about the beach rising after the disaster. Those details sound remarkably familiar today. They're exactly the kinds of things scientists expect to see after a shallow earthquake, followed by a local tsunami. For generations, those stories were treated as oral history. Now they look a lot more like eyewitness accounts. That's what makes this so fascinating. Science didn't replace the old stories. It helped explain them. And suddenly, what many people once dismissed as legend began to look like the preserved memory of a real disaster that happened more than 1,000 years ago. This is the moment the whole story took a completely different turn. The scientists weren't just looking at random clues anymore. They started following the landscape itself. At Restoration Point, they noticed something unusual. The ground wasn't gently sloping like it should have been. It looked like someone had lifted one side of the shoreline several yards higher than the other. They kept walking. The raised ground stretched on for a long distance, almost like it was following an invisible line. Then, just as suddenly, it ended. On one side, the land sat much higher. On the other, it dropped back down. It wasn't gradual. It was sharp enough to make them stop and ask why. So they traced that line on a map, and that's when everything changed. Instead of ending at the shoreline, the line continued beneath Puget Sound. It crossed the water and pointed straight toward downtown Seattle. Not around the city, right through it. That realization must have been hard to ignore. The fault wasn't hiding somewhere out in the mountains or far offshore. It ran beneath one of the busiest parts of the city, where thousands of people work, live, and travel every single day. Even more surprising, several of Seattle's best-known high-rise buildings had already been completed before anyone understood this fault was there. Now, that doesn't automatically mean those buildings are unsafe or that they're going to collapse in a future earthquake. That's not what the evidence says. But it does mean the engineers who designed them couldn't account for a hazard that hadn't been recognized yet. And honestly, they couldn't have. You can't solve a problem that nobody knows exists. That's the part that really stuck with me. A building can look modern. It can represent the latest engineering of its time, but science keeps moving forward. Sometimes our understanding of the ground beneath a building changes long after the building itself is finished. In that sense, the structure doesn't become weaker. Our understanding simply becomes stronger. In late 1992, researchers published their findings, showing clear evidence that the Seattle fault was real. Soon after, hazard maps began to change. What had once been considered stable ground was now recognized as part of an active fault system. The city hadn't changed overnight, but the way people understood the ground beneath it had. Once scientists confirmed the Seattle fault was real, you might think everything changed overnight. It didn't. The first reaction was much more complicated than that. Back in the early 1990s, researchers knew the fault existed. But knowing a fault isn't the same as knowing exactly what it can do. The computer models at the time were still pretty limited. They could identify the fault, but they couldn't fully show how the ground would move or how an earthquake would affect a city built right on top of it. So when officials described the risk as manageable, that didn't mean the danger was small. It meant something very different. It meant building codes would gradually improve. Bridges would be studied. Critical infrastructure would be upgraded over time. Older buildings would be strengthened whenever funding and priorities allowed. That's what manageable looked like in the real world. And honestly, that's how most cities deal with long-term risks. There's a big difference between discovering a problem and solving it. First, you have to prove the fault exists. Then you have to understand how it behaves. After that, you have to figure out how thousands of different buildings might respond. And even if you know the answers, you're still faced with another challenge. Time, money, resources. No city can rebuild itself all at once. That's why I don't think this story is really about a cover-up. It's more about how science often moves faster than everything around it. Researchers can publish new discoveries in a matter of months. Updating building codes takes years. Retrofitting bridges takes even longer. Replacing old buildings can take decades. The science changes first. The city changes much more slowly. But then something happened that completely changed the conversation. As computer technology improved, researchers were finally able to build detailed simulations of a large Seattle fault earthquake. And what those models revealed was something almost nobody had expected. The ground beneath downtown Seattle wouldn't just shake. In some places, it could actually make the shaking even stronger. This is where the story gets even more interesting. The fault itself isn't the only concern. The ground beneath downtown Seattle plays a big role too. A lot of the city's downtown sits on layers of soft soil, old river sediments, and land that was filled in over the years. That kind of ground doesn't behave the same way as solid bedrock. When earthquake waves travel through hard rock, they move differently than they do through soft soil. As those waves enter softer ground, they can slow down, build up, and keep moving longer than you might expect. A simple way to picture it is with a wine glass. Tap the rim once, and the sound doesn't stop immediately. The glass keeps ringing for a while. Some researchers believe parts of downtown Seattle could respond in a similar way during a major earthquake. The strongest shaking might be over, but the soft sediments could continue to move as they absorb and release energy. That matters because not every structure reacts the same way. Tall buildings tend to respond differently than shorter ones. Bridges, seawalls, pipelines, and port facilities all have their own weak points. Ground that was created by filling in old shoreline areas may also be more vulnerable to problems like liquefaction, where saturated soil temporarily loses much of its strength during intense shaking. Even things people rarely think about can become hazards. Glass can break. Exterior walls can fail. Heavy furniture or equipment that isn't secured can move unexpectedly. None of this means downtown Seattle would automatically be destroyed. That's not what the research says. What some computer models suggest is that shaking in areas with soft sediments could be much stronger than it would be just a few miles away on solid rock. In other words, where you are standing can make a big difference, even within the same earthquake. Then, in 2001, Seattle experienced another important moment. The Nisqually earthquake gave people a real-world reminder that the region was active, but it also created a new question. Did that earthquake really show what the Seattle fault is capable of, or was it a completely different kind of event? The Nisqually earthquake in 2001 changed the conversation. For a lot of people, it became proof that Seattle could handle a major earthquake. The city shook, there was damage, but life went on. It's easy to understand why that gave people confidence. The problem is, Nisqually and the Seattle fault are not the same kind of earthquake, not even close. The Nisqually earthquake happened deep underground, more than 30 miles below the surface. By the time those seismic waves reached Seattle, they had already traveled a long way and lost a good amount of their energy. The Seattle fault is different. It's much closer to the surface, and it runs beneath the metropolitan area itself. If that fault ruptures, the shaking begins much closer to where people actually live and work. That difference matters. Two earthquakes can have similar magnitudes and still produce very different results. Depth matters. Distance matters. The type of ground beneath a city matters. Even the direction the fault breaks can change how the shaking spreads. That's why scientists don't compare earthquakes by magnitude alone. What really stayed with me is how people naturally think. When you've already been through something difficult and survived, it's easy to believe you've seen the worst. Seattle experienced a significant earthquake in 2001, and the city didn't collapse. For many people, that became a kind of reassurance, almost like the city had already passed the test, but in reality, it wasn't the same test. The Nisqually earthquake wasn't a direct preview of what the Seattle fault could do. It was a different earthquake, with different conditions and a different source. That's an important distinction. Surviving one kind of disaster doesn't automatically mean you're prepared for another. While that public confidence continued, Seattle kept growing. New buildings went up. Development continued. Building codes gradually improved as researchers learned more about the fault and how it behaves. That's usually how progress happens. Science moves forward one discovery at a time, and cities adapt one project at a time. The challenge is that the Earth doesn't wait for construction schedules or budget cycles. It follows its own timeline. Just when it seems like you've figured out the Seattle fault, the story gets even bigger. As mapping technology improved, scientists got a much clearer picture of what was hiding beneath the Pacific Northwest. One of the biggest breakthroughs came from LiDAR. It's a laser scanning system that can strip away trees and vegetation in digital maps, revealing the shape of the land underneath. Features that are almost impossible to see from the ground suddenly become obvious. And that's exactly what happened around Puget Sound. Researchers realized the Seattle fault wasn't an isolated crack in the Earth. It was part of a much larger system. They identified several other shallow faults across the region, including the Tacoma Fault, the Southern Whidbey Island Fault, the Devil's Mountain Fault, and the Saddle Mountain Fault. Each one has its own history. Each one has its own behavior. But together, they paint a much more complicated picture. Some geological evidence suggests that more than one of these faults may have been active within roughly the same period in the past. That doesn't mean they'll all rupture together in the future. Nobody can say that. But it does remind us that these faults don't exist in complete isolation. They're part of the same regional system, and scientists continue to study how they might influence one another over very long periods of time. That completely changed the way I thought about the risk. Instead of imagining one fault running beneath one city, it's more accurate to picture an entire network beneath one of the most populated parts of the Pacific Northwest. It's a much bigger puzzle than it first appears, and honestly, that's what makes this story so fascinating. The more researchers learn, the more they realize how much is still unknown. But here's something worth remembering. Even if only the Seattle fault were to rupture, the first thing people would experience wouldn't be the tsunami. It would be the shaking. Roughly 40 seconds, where the ground no longer feels solid, familiar, or predictable. For those few moments, everything people usually trust the most, the ground beneath their feet, could suddenly become the one thing they can't rely on. When I tried to picture what a Seattle fault earthquake might actually feel like, I realized it probably wouldn't unfold the way most people imagine. It wouldn't start with a tsunami. It would start with the ground. Because this is a shallow fault, a lot of the energy would be released close to the surface. The shaking could become intense almost immediately. During those first moments, running probably wouldn't even be your first option. Your biggest challenge would simply be staying on your feet. Inside buildings, furniture could slide, glass could break, bricks, signs, and pieces of building facades could fall into the streets. Power could go out, water lines might break. Cell service and communications could become unreliable just when people need them the most. Then comes the part many people don't think about. Even after the strongest shaking begins to fade, the ground beneath parts of downtown may continue moving because of the soft sediments below the city. That means some buildings could keep swaying longer than people expect. Bridges, elevated roads, and underground utilities could all be dealing with different kinds of stress at the same time. And while all of that is happening, emergency crews may still be trying to figure out which roads are open and which ones aren't. The first few minutes after a major earthquake are often just as confusing as the earthquake itself. Then there's the water. Because the Seattle fault runs beneath part of Puget Sound, movement along the fault could displace the water above it and generate a local tsunami. Unlike a tsunami that begins far offshore, this one wouldn't have to travel very far. The warning time could be extremely short. That's what makes it so different. A wave that's only a few yards high doesn't always become a major disaster by itself. But if it reaches the shoreline right after a powerful earthquake, when roads are damaged, bridges may be closed, power is out, and communication is disrupted, the situation changes completely. The wave isn't arriving at a city that's functioning normally. It's arriving at a city that's already struggling to respond. There's one more thing that's easy to forget. A tsunami isn't always just one wave. Water can come in more than one surge, with later waves sometimes arriving after the first one. That's why emergency officials often remind people not to return to the shoreline too quickly. The danger may not be over just because the first wave has passed. One thing about the Seattle Fault really stayed with me. It's how quiet it has been. Since scientists identified it, the fault has produced very few noticeable earthquakes. There have been small events here and there, but nothing that clearly hints at a major rupture. At first, that sounds reassuring, but the more I looked into it, the more I realized silence doesn't really tell us what we want to know. A quiet fault isn't automatically a safe fault. At the same time, it doesn't automatically mean the fault is storing every bit of stress for one huge earthquake, either. The truth is more complicated than that. Different faults behave in different ways. Some slowly release stress through gradual movement or frequent, small earthquakes. Others can stay locked for very long periods before moving again. The Seattle Fault hasn't given scientists a simple pattern they can rely on. That's why researchers also pay close attention to GPS measurements across the region. These instruments are incredibly precise. They can detect tiny movements in the Earth's crust that are far too small for people to notice. The data shows that the Pacific Northwest is still being squeezed by tectonic forces. The land on opposite sides of the Seattle Fault continues to move relative to each other over time. That tells us the region is still active. But it's important to understand what GPS can and can't do. It measures slow movement across large areas. It is not a countdown clock for earthquakes. Sometimes people hear numbers like a few millimeters of movement each year and assume you can simply add them up until the fault finally breaks. It doesn't work that way. The Earth's crust is far more complicated than filling a gas tank until it reaches a certain line. Stress builds unevenly. Rock behaves differently at different depths. And scientists still don't fully understand what finally triggers one fault to rupture while another remains quiet. So, I think the most honest way to look at this is also the simplest. The Seattle Fault is an active fault. The region is still being shaped by tectonic forces. But no one-not scientists, not engineers, not anyone else can tell you the exact day, month, or even year when the next major earthquake might happen. That's probably the hardest part of this entire story. Not knowing doesn't mean nothing is happening. It simply means nature isn't following a schedule that humans can read. Out of everything I learned about the Seattle Fault, this might be the image I can't get out of my head. Deep beneath Lake Washington, there are trees still standing underwater, not broken apart, not scattered across the lake bed. They're still upright, almost exactly where they once grew. One explanation is that a section of land slid into the lake during an ancient earthquake, taking the forest with it. The cold water and low oxygen at the bottom helped preserve those trees for centuries. It's like the Earth kept a photograph of that moment. When I first saw pictures of them, they didn't look like evidence. They looked like a frozen memory. The lake holds another clue, too. Scientists have studied layers of sediment at the bottom and found sections that appear to have been disturbed by strong shaking. Those layers may record ancient earthquakes that happened long before written history. Some of the evidence even suggests there may have been more than one major event within a relatively short period of time. But it's important to be careful here. The geological record isn't perfect. Dating ancient sediments always comes with some uncertainty, and researchers are still working to understand exactly how these events fit together. What we can say is that the history of this fault doesn't look simple. It doesn't appear to follow the kind of regular cycle people naturally hope for. There may have been earthquakes that happened fairly close together. Then came a silence that lasted more than 1,000 years. That's hard for us to wrap our heads around. As people, we like patterns. We like calendars. We want to believe nature works on a schedule we can understand. But geology doesn't really care about our timelines. Those trees tell that story better than anything else. Some of them may have started growing after an earlier earthquake. They survived for generations, growing quietly while people rebuilt their lives around them. Then another major earthquake came. The ground moved again, and the forest disappeared beneath the water. When you think about it like that, you realize how short a human lifetime really is. A fault can stay quiet long enough for dozens of generations to come and go before it moves again. That's why the silence can be misleading. It doesn't tell us when the next earthquake will happen. It only tells us that the last one happened long enough ago for people to forget. The fault doesn't keep time the way we do. It leaves behind evidence. And we usually don't recognize what it means until long after the day itself has passed. After learning all of this, I don't walk away thinking Seattle is doomed. I actually walk away thinking people have been making progress. Building codes today are much stronger than they used to be. Newer buildings are generally designed with better earthquake knowledge than older ones. Some seawalls, bridges, ferry facilities, and other critical infrastructure have already been rebuilt or reinforced. The city has hazard maps, emergency plans, and earthquake drills. That's real progress. But it's also true that no city can rebuild everything at once. Thousands of older buildings are still standing. Many were designed long before the Seattle fault was fully understood. Replacing or retrofitting every one of them would take decades, enormous funding, and countless difficult decisions. And a city isn't just made of buildings. Everything is connected. Electricity depends on substations and transmission lines. Water depends on pipes and pumping stations. Roads connect to bridges. Hospitals rely on power, communications, and transportation. A city is really one giant system, and like any system, it's only as strong as its weakest parts. That's why I think preparation matters more than prediction. None of us can control when the next earthquake happens. But we can control how ready we are if it does. Even simple things make a difference. Know roughly when your home or workplace was built. Secure heavy bookshelves, cabinets, water heaters, and anything that could fall during strong shaking. Keep enough water, basic medicine, flashlights, batteries, and emergency supplies to get through several days if services are interrupted. Remember the basic rule during an earthquake: drop, cover, and hold on. If you're near the shoreline and you've just felt strong shaking, don't wait for someone to tell you what to do. Move to higher ground as soon as it's safe to do so. Stay away from windows, damaged walls, and the outside of buildings until the shaking has completely stopped, and don't assume your phone will always work. Have a plan for how your family will reconnect if cell service goes down. For me, that's really what this story is about. The next earthquake isn't dangerous because we don't know the exact day it will happen. It's dangerous because a modern city has to make thousands of decisions during the long, quiet period between earthquakes. That quiet could last another 100 years. Or it could end on an ordinary afternoon when nobody is expecting it. The goal isn't to predict the exact day. It's to make sure we don't spend today acting like the risk was never there in the first place.